This is part 3 of a series of videos on the Foenix F256 and the 6809. In this video, I'll go deeper into the OS9 I/O system. In the previous video, I used this slide to illustrate the OS9 I/O system organization. The concept of unified I/O rests on the notion of a single entity called a path. File is the object on that path. IOMan is at the top and the file managers sit just below it in green. IOMan creates the I/O world and orchestrates related system calls, but delegates the actual organization and work of specific classes of devices to file managers. File managers further delegate the work of interfacing with specific hardware to the device drivers in blue, and the device descriptors in purple are modules that contain configuration information as well as the name of the file manager and driver for a specific instance of a device. IOMan expects file managers to implement 13 specific entry points related to file input and output. Files can be created, opened, deleted, seeked into, read and written from, and closed. Read line and write line entry points handle reading and writing data up to a line ending character such as the carriage return. And since files can be directories, there are 2 entry points for creating and changing into a directory. Finally, the get status and set status entry points are hooks that allow for additional functionality through status codes. Drivers interface with file managers and define 6 entry points. The initialization entry point is where the driver performs any actions to prepare the device for work, such as setting up its state and installing an interrupt handler if needed. The read entry point is where the driver obtains data from device to ferry up to the file manager. The write entry point is where the driver writes data provided by the file manager to the device. The get stat and set stat entry points are for supporting getting and setting the status of the device, and the termination entry point is where the driver uninstalls a previously installed interrupt handler and sets the device to a non-working state. The first file manager I'll survey is RBF, which stands for Random Block File Manager. RBF's file system is hierarchical, like Unix. Files contain bytes of data that reside in directories, and directories can contain files in other directories. RBF attaches no significance to a file's content. A file can contain image data, text, or even an OS9 module. To RBF, it's just a stream of bytes. Files do have attributes, which are analogous to Unix file permissions. I'll explore that shortly. Finally, file names are case insensitive in RBF and can be up to 29 characters in length. A unique feature of OS9 is the separate concept of the data and execution directory. While processes under Unix track a single current directory, IOMan enforces the tracking of 2 directories per process, the data directory and the execution directory. The data directory is analogous to the current directory on Unix and defaults to the root device at boot time. You use the chd command from the shell to change this directory, just as you would use the cd command on Unix. The execution directory has no analog to Unix. It defaults to the commands directory, and you use the chx command from the shell to change it. The execution directory is where IOMan searches for programs to load and execute. Here are some additional file-related commands that you can try on OS9. Free shows the free space on a device, similar to df on Unix. Use copy to make copies of files like cp on Unix. To change the name of a file, use rename, similar to mv on Unix. Del deletes a file like rm does under Unix. Makedir is analogous to mkdir on Unix. To delete a directory, use deldir on OS9. It's a separate command unlike rm-rf in Unix. File attributes under OS9 are modifiable with the adder command, similar to chmod under Unix. But it's been some time talking about some RBF commands that are important to understand and useful when you use OS9. First command is dir, which we've seen before. dir shows the contents of a directory. And I can type a path list, a partial path list, a relative path list like sys in this case, which is a directory, or sounds, things like that. The other thing I can do is I can do a dir-x, which shows the execution directory contents. And -x, remember, we used this on another command as well earlier, will always do something relative to the execution directory. Well, if we look at what our execution directory is, we can see that by typing pxd. It's /dd/commands. /dd happens to be the device that we're on at the moment. pwd is the data directory, which is analogous to what is under Unix. So if I chd to sys, which is relative to my root directory, and then type pwd, you'll see that I'm in now dd sys, and when I type dir, I look at the contents of the sys directory. So I'll chd back so that my data directory is at the root. And let's look at the, we looked at the pxd command earlier. Let's actually chx up one folder from where our execution directory is. And when I do that, my execution directory is now the root. And if I type pxd this time, you'll notice I get an error 216, which means file not found. It means that the operating system could not find the pxd command. Why? Because it was in the commands directory, and now our execution directory is no longer there. Now I can execute the command by using a full path list to the location of the command. And you can see now that our execution directory is at the root. So what I'll do is I'll chx back into the commands folder, which is relative to where we just were. And now if I type pxd, you'll notice that the command works. I'm going to dump a file here. So I mentioned that a file in RBF is just that, a flat series of bytes. It doesn't care what's in it. But if I do a dir-x and look at the files here, you'll see file names associated with commands that we run, like mdir, mfree, and so on. So what I'll do is I'll dump a small command, and I'll dump it relative to the execution directory, and I'll dump t. And as you can see, the t file in the commands directory is an OS9 module inside. You see the 87cd sync bytes at the beginning. So the files inside of the execution directory, the commands directory, are all files that contain OS9 modules. So when you type the command at the shell prompt, the system goes and looks for that file of that name in the execution directory first, attempts to load it into memory and execute it as a module. We talked about file managers and device drivers. Let's take a look at the device descriptors in memory that we have. Now, we talked about how a device descriptor maps or binds a file manager to a driver for an instance of a device. Since we're on the DD device, let's dump in memory the DD device descriptor. And you can see in the text on the right that at offset 2A is the DD name. That's the name of the module, at 2A. And beyond that, you see at 2C is RBF, which is the name of the file manager. And then the driver at offset 2F is RB super. So that is the binding that you see happening where the device descriptor ties all that together. This device descriptor also happens to bring in the name of the low-level module, the subroutine module for RB super, called LNFNX-SD. And that's specific to the actual RB super driver. But that's what a device descriptor does. It binds all of the modules together and says, hey, to IOman, for this device, this is the file manager and the device driver that this device uses. A couple of other commands that we'll look at. I'll chd to the BF directory. List is similar to cat. It shows the contents of a text file. And as you can see, it just listed that file out. If I do a dir-e to get an extended directory, it's going to show interesting things about each file that's in this directory. And you'll notice the third column is the attributes. I mentioned that in the previous slide. These are the attributes that allow either the owner or the public to execute, read, or write a file. I will use the adder command, and I will change the attributes of inout.bf so that the public write is set. And when I do that, you'll notice it put out -WR and -WR. And when I do a -E again, now the public writable attribute is on, which means that someone other than the owner of this file could actually write to it. And the way you turn that off in Adder is you specify a dash in front of the option you want to turn off, and that is now gone. One final thing I want to do is I want to use a special command called dead. And if I do dir-x, you'll see that dead is on the first column, third row there. It's a command that allows us to look at files in a hex dump interactively. I'm going to do something special here. I'm going to look at the /dd at device. This is the actual root device. The at means open up the device as an entire file. And what we're looking at right now is the actual sector 0 of the SD card. So we're looking at the raw file system that RBF produces. And in RBF, all sectors are 256 bytes. Even though the physical device might be a 512 byte sector device like an SD card, RBF is presented with 256 byte sectors. So the first sector here that you see is the root sector, the identification sector for an RBF device. And I won't go into the details here, but you can see the name of the device is Nitrous 9 6809 level 1. That's actually the name of the volume. And we get to the first directory here. This is the root directory, and this ought to look familiar because these are the files that you see when you type dir at the root directory. So you can get an idea by typing this command to explore what a disk looks like from the very basic sector by sector level. SCF is the Sequential Character File Manager. It manages character-based devices, such as video terminals, built-in text screens, printers, and serial ports. Now let's take a look at some SCF devices. I'm going to type mdir. We have a few in the module directory. We have term, we have T0. I'm going to dump T0. And you'll see that its device name is T0 at offset 2E. The file manager at offset 30 is SCF, and the driver at offset 34 is SC16550. So again, just like RBF, an SCF device descriptor ties in a file manager with its driver and the specific instance for this device, which would be the serial port on the F256. I mentioned the tmode command, and tmode is a lot like STTY under Unix. It allows you to set options for your device, and the current device we're interacting with is the term device. For instance, I can set UPC, which is uppercase, to 1. And now when I set that flag to 1, everything I type in all my output becomes uppercase. So there might be some reason you want to do that. We'll change that back to 0, and we're back to lowercase. There are some other things here. For instance, echo is 1. If I type tmode echo equals 0, now when I type something, it doesn't echo what I type back to the screen. So I'll type that, or turn that back on by typing echo equals 1. Automatic line feed will produce, ALF will produce an automatic line feed for each carriage return. If I turn that off, then you'll notice that everything just goes on one line, and that's not going to be visually pleasing, so I'll put that back on. There's also some other values here, end of record, which is D for carriage return, BSP for backspace. Anyway, these are all documented, and you can look and see how these change for change an SCF device. The other command is xmode. Now, xmode works on device descriptors. You have to pass the device descriptor. In this case, I'm passing in T0. I could change things about the T0 descriptor, similar to what I did with tmode. And then when I open that descriptor for some use, then it will actually apply those options to that open path. SCF devices can be customized to a certain degree. For instance, You can change the new line character for a device, or its backspace character, or force text to appear in all uppercase. On the F256/T0 is the device for the built-in serial port, and /term is the device for the built-in video text screen. The T-mode command lets you change options on the current device, which is usually the video terminal, and is similar to STTY under Unix. X-mode lets you change the options on an SCF device descriptor before it's used to open a path to a device. T-mode and X-mode have very similar options. The final manager I'll talk about is Pipeman. This file manager implements an interprocess communication method that is similar to Unix. A process can open a path to a pipe, then fork a child process and pass data to it through the path. Pipeman has one driver, named Piper, and one descriptor named Pipe. It's a unique file manager in that all of the processing of the pipe takes place in the file manager itself. The Piper driver is considered a dummy with entry points that do nothing. The pipe file manager also has entry points that do nothing, such as makedir, chgdir, and delete. Pipes under OS 9 work just like they do under Unix, and if you can see the output of the mdir command, there's pipe, man, piper, and pipe on the third row. And what I'll do is I'll demonstrate by loading some commands in memory so they run a little quicker. We'll load in grep, and we'll load in mdir. And to prove that they're there in memory, you can see that there's grep and mdir at the last line. So let's do an mdir-e, and let's find every line that has X in it, or the capital X. And the way we do that is we do mdir-e, and we use the pipe symbol on the shell, which is the exclamation point, and we'll grep for capital X. And as you can see, the output of mdir-e was shunted by the grep command. The grep command filtered out any line that didn't have capital X in it. And this is how pipes work in OS 9. You can even go and add another one and add another instance of grep and only filter out anything with the letter 0. And as you can see, well, every line has 0, so let's try something maybe 1 and see what happens there. Every one line has 1 as well. How about 2? And how about 3? How about 5? Something like that. There we go. So there you can see how pipes can be concatenated just like they can under Unix. So very powerful, very useful feature. And an application can actually open the /pipe device and set up input and output and pipe data from one process to another process that it might fork. Very convenient. To summarize, IOMan creates the IO world for OS 9. It defines the entry points and data structures for the file managers that live beneath it. IOMan delegates class-specific functions to those file managers. File managers exist for things like block devices, sequential character devices, and pipes. File managers delegate device-specific work to device drivers. Device drivers are modules that know how to talk to a specific type of device, such as a specific serial port or a specific disk driver. Device descriptors tie together file managers and device drivers to define an instance of a device.